There is a moment, far beyond the orbit of Earth, when the solar system changes. Nothing marks it. There is no wall suspended in the darkness. No warning signal arrives through the spacecraft. No sudden boundary appears beneath the stars. You simply pass the orbit of Neptune, and for the first time since leaving the Sun, there is no longer another planet waiting ahead. Behind you, Neptune is slowly shrinking into the distance. Its deep blue atmosphere, once large enough to fill the windows of the spacecraft, has become a small sapphire circle against the black. Its clouds still move at extraordinary speeds. Storm systems still sweep through an atmosphere colder than almost any place found among the planets. Faint rings continue to surround it, and its moons follow their ancient paths. But with every passing hour, those details become harder to see. Soon, Neptune is no longer a world. It is only a point of blue light. Farther behind it lie Uranus, Saturn, Jupiter, Mars, Earth, Venus, and Mercury. All 8 planets now occupy the same general direction in the sky. Every ocean, every city, every living forest, and every human being exists somewhere inside that distant point of space behind you. Ahead, there is no 9th planet waiting in the darkness. There is no enormous world reflecting sunlight back toward your instruments. No bright moon crosses your path. No planetary magnetic field surrounds the spacecraft. No destination announces itself. There is only space. And it continues much farther than almost anyone imagines. Most diagrams of the solar system create a comforting illusion. They place the planets close together, each one separated by a manageable stretch of darkness. Neptune appears near the edge of the page, with Pluto sometimes drawn just beyond it. After that, the illustration usually ends. It is easy to believe that the solar system ends there as well. But Neptune is not the edge. It is the last place where the solar system still looks familiar. For billions of miles, the planets have provided structure. They divide the darkness into recognizable regions. Mars marks the beginning of the colder worlds. Jupiter announces the domain of the giants. Saturn carries its rings like a landmark visible across the void. Uranus turns on its side. Neptune waits at the end of the planetary road. Once Neptune falls behind, that road disappears. The spacecraft has entered a region where distances are no longer measured from one planet to the next. They are measured between small, dark objects that may be separated by millions of miles. This region is often described as the outer solar system, but even that phrase can be misleading. It sounds like a narrow border surrounding the planets, a final layer that can be crossed before reaching interstellar space. In reality, the space beyond Neptune is larger than the entire planetary system you have already traveled through, and Neptune is only the beginning. Out here, the sun remains visible. It is still brighter than every other star, but it has become small enough to cover with the tip of a finger held at arm's length. Its light needs more than 4 hours to reach Neptune, and even longer to reach the regions beyond. That light still illuminates the spacecraft, but it carries almost no warmth. The sun that once warmed Earth's oceans, powered its winds, and supported nearly every living thing has become a brilliant point in the distance. It can still show you where home is. It can no longer make the darkness feel safe. The temperature outside the spacecraft is only a few dozen degrees above absolute zero. Materials that behave like gases on Earth freeze into hard surfaces. Nitrogen becomes ice, methane becomes solid. Water becomes stronger than stone. Yet the cold is not the most disturbing part of this journey. Neither is the darkness. The true problem is that almost everything humanity depends on begins to weaken once Neptune is behind you. Sunlight becomes too faint to provide useful power. Radio messages take hours to cross the distance. A spacecraft cannot be controlled in real time. If a system fails, no engineer on Earth can immediately respond. No rescue mission can arrive. No nearby planet can provide shelter, gravity, or resources. And even the map ahead becomes uncertain. Beyond Neptune lies a vast population of frozen objects left over from the formation of the solar system. Some are small enough to fit beneath a city. Others are large enough to become round worlds with moons, atmospheres, mountains, glaciers, and perhaps even hidden oceans. Thousands have been discovered. Hundreds of thousands more may remain unseen. But do not imagine a crowded field of ice and rock. Do not imagine the spacecraft weaving between tumbling objects as it would in a science fiction movie. The reality is more unsettling. This region can contain countless worlds and still appear completely empty. A spacecraft could travel through it for years without passing close enough to see even one of them with the naked eye. Each object is separated from the next by an expanse so large that the mind struggles to treat them as members of the same belt. There may be more matter ahead than our maps once predicted. There may be entire populations of objects too dark and too distant for our telescopes to detect. And there may be forces written into their orbits that point toward events, and perhaps worlds, we have never witnessed. Neptune is now fading behind you. The last great planet has become another light among the stars. Ahead lies no clear border, no final destination, and no obvious moment when the solar system will truly end. Only a frozen frontier that looks empty from the inside. And that appearance is the first deception of the space beyond Neptune. Before Neptune disappears completely behind you, it is worth understanding what has just been left behind. Neptune is not simply the eighth planet. It is the final giant world in the solar system, the last massive body whose gravity dominates an entire region of space. Beyond it, there are no more planets large enough to organize the darkness in the familiar way. Neptune circles the Sun at an average distance of about 2.8 billion miles. That number is difficult to feel. So imagine sunlight leaving the surface of the Sun. It crosses the orbit of Mercury in a little over 3 minutes. It reaches Venus in about 6. It arrives at Earth after 8 minutes and 20 seconds. By the time that same light reaches Jupiter, more than 40 minutes have passed. At Saturn, the journey has taken well over an hour. At Uranus, nearly 3. Neptune waits more than 4 hours from the Sun. If the Sun suddenly vanished, not that it could, you would continue to see it shining from Neptune for more than 4 hours before the final light arrived. Earth would already have been dark for most of that time. The same delay governs communication. A radio signal sent from Earth to a spacecraft near Neptune cannot arrive in a few seconds, or even a few minutes. It must travel across billions of miles of nearly empty space. Depending on the positions of Earth and Neptune, the journey takes roughly 4 hours one way. A command sent in the morning might not reach the spacecraft until the afternoon. If the spacecraft answered immediately, the reply might not return until late in the evening. There can be no conversation, only messages. Each one is launched into the darkness, followed by hours of silence. At this distance, Neptune still receives sunlight, but only a tiny fraction of the energy that reaches Earth. Because light weakens with the square of distance, moving 30 times farther from the Sun does not make sunlight 30 times weaker. It makes it about 900 times weaker. The Sun above Neptune is still far brighter than the other stars. It can cast shadows. It can illuminate clouds and rings. It can reveal the pale surface of Triton, Neptune's largest moon. But its warmth has almost vanished. Neptune's upper atmosphere falls to temperatures near -350 degrees Fahrenheit. The planet is colder than Uranus in some regions, even though Uranus lies closer to the Sun. And yet Neptune is not quiet. Its atmosphere contains some of the fastest winds ever measured in the solar system. Dark storms form and disappear. Bright clouds of frozen methane race through the upper atmosphere. Weather continues beneath sunlight too weak to warm a human hand. This is one of the first lessons of the outer solar system. Cold does not mean stillness. Distance does not mean simplicity. Neptune itself is evidence of that. But as remarkable as the planet is, its greater importance to this journey lies in where it stands. For most of human history, Neptune was not known to exist. It was discovered not because someone happened to notice it wandering across the night sky, but because another planet was behaving incorrectly. Astronomers studying Uranus found that its orbit did not quite match their calculations. Something unseen appeared to be pulling on it. By using mathematics, they predicted where this hidden object should be. In 1846, telescopes were pointed toward that position. And Neptune was found. A planet had been discovered through gravity before it was clearly recognized through light. That history gives Neptune a fitting role at the edge of the planetary system. It is a world whose presence was first revealed by an invisible force. And beyond it, invisible forces become even more important. Neptune's gravity extends far past the blue clouds of the planet itself. It reaches into the frozen populations beyond, shaping orbits, trapping some objects into stable patterns, and scattering others into the distant darkness. Even after Neptune becomes too small for the eye to distinguish, its influence remains ahead, but the visual presence of the planet is disappearing quickly. At first, Neptune may still appear as a tiny blue disk through the spacecraft's instruments. Then it becomes a point. Later, it is difficult to separate from the field of background stars. There is something deeply strange about watching a planet become a star. A planet is a place. It has weather, gravity, moons, seasons, and a surface or atmosphere that a spacecraft can approach. A star-like point is only a direction. As Neptune fades, the final recognizable landmark in the solar system is being reduced to a coordinate behind you. The sun still marks the center, but the planets no longer divide the road ahead. On Earth, distance is often understood through destinations. A road connects one town to another. A flight crosses the space between two cities. Even an ocean voyage is defined by the land that waits at the far side. Beyond Neptune, there is no equivalent. The next known object may be millions of miles away and far too small to see. The next large world may lie in a completely different direction. The spacecraft is not traveling from planet to planet anymore. It is traveling through a volume. This difference matters. The outer solar system is not arranged like a line of stepping stones. It is a vast three-dimensional wilderness filled with small bodies on different inclinations, different eccentricities, and different orbital periods. Some travel close to the same broad plane as the planets. Others rise high above it. Some remain beyond Neptune at all times. Others follow elongated paths that carry them inward toward Neptune before sending them hundreds of times farther from the Sun. And almost all of them are nearly invisible. At Neptune, the solar system still presents one final enormous object, a world 4 times wider than Earth, surrounded by moons and marked by storms. Just beyond it, the scale collapses. The next bodies are smaller, darker, and far more widely separated. The gravitational architecture is still there, but the landmarks are gone. This is why Neptune feels like an ending, even though it is not one. It is the end of the solar system as a sequence of planets. It is the end of the region where the largest objects are easy to identify. It is the last place where a traveler can look ahead and expect another world of comparable scale to be waiting. But the space beyond is not empty. It is filled with remnants from the birth of the solar system, worlds that never became planets, fragments that survived ancient migrations, and objects whose orbits preserve events that happened billions of years before Earth had oceans. Neptune is not the final chapter. It is the final familiar page. And as that blue point fades behind the spacecraft, the next region begins to reveal its most unsettling quality. It contains an enormous number of objects, yet from inside it, you may see none of them at all. The region beyond Neptune is usually drawn as a ring, a thick band of icy objects surrounding the Sun, packed together like stones along the edge of a road. From a distance, the image seems reasonable. Thousands of known bodies occupy this part of the solar system, and many more are believed to remain undiscovered. Pluto is here. So are Eris, Makemake, Haumea, Quaoar, and countless smaller worlds left over from the formation of the planets. But if your spacecraft were traveling through the Kuiper Belt now, the view outside would not resemble the diagrams. You would not see a wall of ice. You would not see hundreds of objects drifting past the windows. You would probably see nothing at all. The Kuiper Belt contains an enormous number of bodies, but they are distributed across an even more enormous volume of space. Its main region begins near the orbit of Neptune, about 30 astronomical units from the Sun, and extends outward for tens of astronomical units more. An astronomical unit is the average distance from Earth to the Sun, about 93 million miles. So even a region only 20 astronomical units wide spans nearly 2 billion miles. And the Kuiper Belt is not a thin, flat line. It has depth. Its objects orbit above and below the main plane of the planets, creating a broad three-dimensional zone of darkness. On a map, those objects are often drawn far larger than they should be. Otherwise, they would be too small to see. That distortion creates the illusion of crowding. In reality, the space between neighboring bodies can be millions of miles. A spacecraft could cross large portions of the Kuiper Belt without passing close to anything larger than a grain of dust. Even a world hundreds of miles across could remain completely invisible unless the spacecraft happened to approach it along the correct path. This is not an asteroid field from a movie. There is no constant danger of collision. There is no need to weave between spinning mountains of rock and ice. The more realistic danger is almost the opposite. There is so little nearby that a spacecraft could suffer a serious failure and have no meaningful destination to reach. No moon would appear over the horizon. No planet would wait ahead. No solid object would be close enough to use as shelter, a source of material, or even a point of reference. The belt is populated, but it feels empty. That contradiction is one of the strangest qualities of the outer solar system. Pluto once seemed to stand alone in this darkness. After its discovery in 1930, it remained the only known object beyond Neptune for more than 60 years. For most of the 20th century, school books presented it as the ninth planet, a small and distant world occupying the final position in the solar system. It appeared to be an isolated outpost. Then, in 1992, astronomers discovered another object orbiting beyond Neptune. It was not a moon. It was not Pluto. It was a separate icy body, moving through the same distant region. More discoveries followed. At first, there were only a few, then dozens, then hundreds. Eventually, thousands of trans-Neptunian objects were identified, and Pluto's isolation disappeared. Pluto had not been guarding the edge of the solar system. It had been the first visible member of a vast hidden population. The reason these objects remained undiscovered for so long was not that they were rare. It was that they were extremely difficult to see. Most are small. Many have dark surfaces that reflect only a tiny fraction of the already weak sunlight reaching them. They move so slowly across the sky that, in a single telescope image, they can be almost indistinguishable from distant stars. To find one, astronomers must photograph the same region of sky repeatedly. Then they search for a faint point of light that has shifted by a barely noticeable amount. A star remains fixed. A Kuiper Belt object moves, but it may move so slowly that the difference becomes visible only after hours, days, or even longer. Every discovery is therefore a small victory over darkness, distance, and patience. And the objects we have found are not necessarily representative of everything that exists there. The easiest bodies to discover are the largest, brightest, and closest. Smaller objects are harder to detect. Darker ones are easier to miss. Bodies on highly tilted orbits may spend most of their time far from the narrow regions where surveys often search. The known Kuiper Belt is not a complete inventory. It is the visible portion of a population shaped by the limits of our instruments. This means the darkness outside the spacecraft may contain worlds that no human being has ever seen. Not because they are hidden behind clouds, not because they emit strange signals, but because they are too cold, too dark, and too far away to reflect enough light toward Earth. Some may be only a few miles across. Others may be large enough for gravity to pull them into spheres. They could have moons, layered interiors, unusual surface chemistry, or geological histories that remain completely unknown. Yet from the spacecraft, they would not appear as dark silhouettes against a bright background. Space itself is already dark. A black object crossing black space is not visible unless sunlight reaches it at the correct angle and enough reflected light enters an instrument. Without that light, a world can exist nearby, in astronomical terms, and still remain absent from the view. The word belt therefore describes a population, not a visual structure. There is no glowing ring surrounding the solar system. There is no clear entrance. There is no moment when the spacecraft crosses a line and suddenly becomes surrounded by frozen debris. The transition is gradual. The orbit of Neptune falls behind. Pluto's region approaches. The number of possible objects increases, but the view remains nearly unchanged. Stars continue to fill the background. The sun continues to shrink, and the darkness between them remains almost perfectly empty to the eye. If the spacecraft passed near Pluto, the situation would change dramatically. A small point would grow into a world. Surface markings would emerge. Mountains, plains, haze layers, and bright fields of frozen nitrogen would appear. But once the encounter ended, Pluto would shrink again. First into a disk, then into a point, then into another unseen object behind the spacecraft. This is how almost every world in the Kuiper Belt exists, from the perspective of a traveler. It is invisible until the narrow moment when distance, direction, and sunlight align. Then it disappears again. The solar system beyond Neptune is not frightening because it is crowded with objects waiting to strike you. It is frightening because it may contain hundreds of thousands of worlds and still offer no visible sign that any of them are there. But these objects are not scattered randomly. Their orbits form families, patterns, gaps, and strange repeating rhythms. The apparent emptiness has structure. And much of that structure was created by the blue planet now fading far behind you. The emptiness beyond Neptune is not random. It has been shaped. Every orbit in this region carries a history. Some objects move in calm, nearly circular paths. Others follow long, tilted routes that carry them far above the plane of the planets. Some approach Neptune's orbit and then retreat. Others remain so distant that Neptune can barely reach them at all. These patterns are the result of gravity acting over billions of years. And the most important sculptor is the planet now disappearing behind you. Neptune does not need to be visible to control the space ahead. Its gravity extends far beyond its atmosphere, beyond its rings, and beyond the orbits of its moons. That influence is weak at great distances, but it has had more than 4 billion years to operate. A small pull, repeated over millions of orbits, can reorganize an entire population of worlds. To understand how this happened, we have to return to the early solar system. The planets did not form exactly where they orbit today. They emerged inside a rotating disk of gas, dust, rock, and ice surrounding the young sun. The inner regions were hot, the outer regions were cold. Countless small bodies formed throughout this disk, colliding, merging, and exchanging momentum. The giant planets grew among them. But their positions were not permanent. As Jupiter, Saturn, Uranus, and Neptune interacted with the remaining debris, they exchanged energy with the smaller bodies around them. A planet could pull on an object and throw it inward. Another encounter could send that object outward. Each interaction changed the object's orbit. It also changed the planet's orbit by a much smaller amount. Over time, those tiny changes accumulated. Neptune gradually migrated outward. It moved through a region once filled with far more icy material than survives there today. As it traveled, its gravity disturbed the objects in its path. Some were scattered inward toward the giant planets. Some were thrown outward into distant, elongated orbits. Some were ejected from the solar system entirely, and some became trapped. This trapping happens through orbital resonance. The phrase sounds technical, but the basic idea is simple. Two objects orbiting the Sun can fall into a repeating rhythm. One completes a certain number of orbits, while the other completes another. Their positions return to the same arrangement again and again. If that rhythm is stable, gravity does not pull randomly. It acts in a pattern. Pluto provides the most famous example. Its orbit is unusual. It is more stretched and more tilted than the orbits of the major planets. For part of each orbit, Pluto is actually closer to the Sun than Neptune. On a simple diagram, their paths appear to cross. That seems dangerous. Two large worlds following crossing orbits should eventually approach each other. A close encounter with Neptune could radically alter Pluto's path, perhaps throwing it inward, outward, or out of the solar system. But this does not happen. Pluto completes 2 orbits around the Sun for every 3, completed by Neptune. This rhythm keeps their closest approaches safely separated. Whenever Pluto reaches the part of its orbit that crosses Neptune's average distance, Neptune is elsewhere. The 2 worlds are connected by gravity, but protected by timing. They have repeated this pattern for billions of years. Pluto is not alone in it. Many other objects share the same general resonance and are often grouped with it as Plutinos. They do not all follow identical paths, but they participate in a similar gravitational rhythm with Neptune. Other resonances exist farther out. Each one can hold a population of small bodies in a particular orbital pattern, creating invisible bands of organization throughout the Kuiper Belt. These structures cannot be seen directly from the spacecraft window. There are no glowing lines marking each resonance. There are no walls separating one orbital family from another. The architecture exists only in motion. To recognize it, astronomers must track objects for years, calculate their orbits, and compare how those orbits relate to Neptune. What appears to be empty darkness is filled with invisible timing. Some objects are protected by it. Others were shaped more violently. Beyond the calmer populations lies the scattered disk. Its members travel on highly elongated and often steeply tilted orbits. A scattered disk object may approach the region near Neptune before moving outward to distances many times greater. These are not worlds following quiet, nearly circular paths. They are survivors of gravitational encounters. At some point in the distant past, they passed close enough to Neptune for the planet to alter their motion. The encounter acted like a slingshot. Some objects gained energy and were thrown outward. Others lost energy and moved inward. A few may have repeated this process several times, wandering through the outer solar system before settling temporarily into their present paths. Temporarily is important. Not every orbit beyond Neptune is stable forever. Some objects may remain in place for billions of years. Others continue to be slowly disturbed. A small change can eventually bring one closer to Neptune again. Another encounter may follow. The object could be thrown farther outward, or it could begin moving toward the inner solar system. Some of the icy bodies that become comets may begin this way. They spend most of their existence in deep cold, far from the Sun. Then a gravitational disturbance changes their orbit. They begin falling inward. As sunlight grows stronger, frozen material on their surfaces begins to turn directly into gas. Dust is released. A tail forms. An object that remained almost invisible for billions of years becomes one of the brightest and most dramatic sights in the night sky. Its appearance near the Sun may last only weeks or months. Then it returns to darkness. In this way, Neptune does more than organize the region beyond it. It can send pieces of that region toward the planets inside. The final giant world acts as both guardian and disruptor. Its resonances protect some populations. Its gravity destabilizes others. It preserves Pluto's path while sending different objects onto journeys that may eventually carry them across the inner solar system. And this process is not finished. Neptune continues to orbit. The Kuiper Belt continues to evolve. Objects still drift into unstable regions. Close encounters still occur. Some bodies will be scattered. Some will be captured into new patterns. Some will eventually leave the sun behind forever. The belt is ancient, but it is not frozen in time. Its structure is still being rewritten, one slow gravitational interaction at a time. This changes the way the darkness should be understood. The space beyond Neptune is not a quiet storage room filled with objects placed there at the birth of the solar system and left untouched. It is the remains of an ancient migration. Its calm regions preserve material that escaped major disturbance. Its chaotic regions preserve evidence of violence. Its resonances are the surviving rhythms of a planet moving outward through a field of ice. Every orbit tells part of that story. And Neptune's role is written everywhere. The planet itself is now far behind the spacecraft. Its blue color is gone. Its clouds cannot be seen. Even its position may be difficult to distinguish without instruments. But ahead, Pluto follows a path Neptune helped stabilize. The scattered objects travel on routes Neptune helped create. The gaps and concentrations in the Kuiper Belt reflect the reach of its gravity. The last planet is no longer beside you, yet its influence surrounds you. And within this architecture of cold, dark orbits are worlds that should have become silent long ago. Somehow, they did not. Somehow, they did not. For a long time, scientists assumed that the worlds beyond Neptune would be simple. They were small. They were cold. They received almost no energy from the sun. Many had spent billions of years in darkness, far from the collisions, sunlight, and gravitational violence of the inner solar system. The obvious expectation was that they had frozen solid long ago. Their surfaces might preserve ancient craters. Their interiors might contain old ice and rock. But nothing important should still be happening. Then humanity finally saw Pluto up close. Before 2015, Pluto was little more than a blurred pattern of light and dark pixels. Telescopes could detect ice on its surface and a thin atmosphere around it, but the landscape itself remained hidden. Scientists knew Pluto was there. They did not know what kind of world it was. When New Horizons arrived, the first detailed images revealed something almost no one expected. Across Pluto's surface stretched a bright, heart-shaped region. Its western half contained an enormous plain called Sputnik Planitia, a basin filled with frozen nitrogen. At first glance, it looked smooth and calm. But the surface was divided into huge polygonal cells, each many miles wide. These patterns were evidence that the nitrogen ice was slowly moving. Warmer ice was rising from below. Colder ice was sinking around the edges. The entire plain was turning over through convection. On Earth, this kind of circulation is associated with liquids, gases, and hot material, deep inside planets. On Pluto, it was happening inside a sheet of nitrogen ice at temperatures only a few dozen degrees above absolute zero. The motion was extremely slow, but it was real. Sputnik Planitia also contained very few impact craters. That meant its surface was not ancient and untouched. It had been renewed. Craters had been erased. The nitrogen ice had shifted, flowed, and resurfaced the basin over geological time. Along the edges of the plain, glaciers of nitrogen moved through valleys and descended from the surrounding highlands. These were not glaciers made from frozen water. At Pluto's temperatures, water ice is too hard to flow easily. It behaves more like rock. Nitrogen, however, can deform. It can creep across the landscape under its own weight, filling low regions and carrying material from one area to another. Pluto has mountains made of water ice and glaciers made of nitrogen. The familiar materials are reversed. The substance that forms rivers, oceans, and clouds on Earth becomes bedrock. The substance that fills most of Earth's atmosphere becomes a moving glacier. Even Pluto's atmosphere refuses to remain still. It is extremely thin, but it changes as Pluto moves around the Sun. When certain regions receive more sunlight, frozen nitrogen turns directly into gas. The atmosphere grows. Winds transport material across the surface. Later, as the seasons change and temperatures fall, the gas freezes again. Pluto breathes on a planetary timescale. Its atmosphere expands and contracts through an orbit lasting nearly 2.5 centuries. A human civilization could rise, change, and disappear during a single Plutonian year. And beneath the surface, Pluto may be even more surprising. Some features appear consistent with cryovolcanism, volcanic activity involving water, ammonia, or other icy materials, instead of molten rock. Large mounds south of Sputnik Planitia may have formed through repeated eruptions from the interior. The evidence is not complete, but the terrain is difficult to explain through impacts or ordinary erosion alone. If these features are truly cryovolcanic, Pluto retained internal heat for billions of years. That raises an important question. Where does the heat come from? The Sun cannot provide it. Sunlight at Pluto is far too weak to warm the interior. Some heat may remain from Pluto's formation. Some is produced by the slow radioactive decay of elements inside its rocky core. Thick layers of ice may trap that warmth more effectively than earlier models assumed. It is even possible that a deep layer of liquid water once existed beneath the crust. Some models suggest that part of it may still remain. A hidden ocean beneath Pluto would not be warm by human standards. It would exist under crushing pressure, sealed beneath many miles of ice, perhaps mixed with ammonia that lowers the freezing point. But even the possibility transforms the image of Pluto. It is no longer a dead ball of ice. It becomes a layered world with a changing atmosphere, moving glaciers, internal heat, and perhaps liquid water hidden in permanent darkness. Pluto was not the first warning. 26 years before New Horizons arrived, Voyager 2 passed Neptune and observed its largest moon, Triton. Triton is unusual because it orbits Neptune in the opposite direction from the planet's rotation. That backward orbit strongly suggests it did not form as a normal moon. It was probably once an independent object beyond Neptune, similar to a large Kuiper Belt world, until it passed too close to the planet and was captured. If so, Triton is a displaced survivor from the same distant population the spacecraft is now entering. Voyager 2 found Triton covered in frozen nitrogen and methane. Its surface was young, with fewer craters than expected. And above that frozen surface, dark plumes were rising into the sky. Geysers of nitrogen gas and dust were erupting several miles upward before high-altitude winds carried the material sideways. The eruptions may have been powered partly by sunlight passing through translucent surface ice and heating darker material below. Even the weak sun at Neptune was enough to drive activity under the right conditions. A world cold enough to freeze nitrogen solid was still producing weather and eruptions. Triton should have prepared us for Pluto. But Pluto was more complicated than even Triton suggested. Not every object beyond Neptune is active in the same way. Some preserve a very different kind of story. In 2019, New Horizons passed a small object called Arrokoth. It was only about 22 miles long and shaped like two flattened lobes joined at a narrow neck. From certain angles, it resembled a red snowman floating in darkness. Arrokoth showed almost no evidence of violent formation. Its two halves appear to have developed near each other inside the same cloud of material. They slowly began orbiting one another, lost energy, and eventually touched at extremely low speed. They did not smash together. They settled together. The collision was so gentle that both lobes survived. This makes Arrokoth something close to a preserved moment from the beginning of the solar system. Its shape records how small planetary building blocks may have formed before the planets existed. In the inner solar system, most objects from that era have been destroyed, melted, buried, shattered, or transformed. Arrokoth remained cold and nearly undisturbed for more than 4 billion years. Pluto and Arrokoth represent two opposite outcomes of the same distant environment. One is large enough to maintain internal activity, cycle gases through an atmosphere, and reshape its surface. The other is small enough to preserve its original structure, almost unchanged. One tells us that cold worlds can remain alive. The other tells us that the cold can protect the past. Together, they reveal why the space beyond Neptune is so scientifically valuable. It is not filled with identical frozen rocks. It contains dynamic worlds, preserved relics, captured moons, dwarf planets, contact binaries, and objects whose interiors may still hold heat from the birth of the solar system. Distance from the sun did not make these worlds simple. It allowed them to become strange in ways the inner planets could not. But all of their motion, chemistry, and hidden warmth survive in an environment that provides almost no energy from outside. The farther the spacecraft travels, the weaker the sun becomes. It is still visible. It is still the brightest object in the sky. But beyond Neptune, light and warmth are no longer the same thing. The sun is still there. From the darkness beyond Neptune, it remains the brightest object in the sky. It is sharper than any star, brilliant enough to stand apart from the constellations around it. But it no longer feels like the sun. On Earth, sunlight and warmth are so closely connected that separating them is almost impossible. Morning light touches the ground, and the air begins to change. Ice melts. Leaves turn toward the sky. Oceans absorb heat. Winds form. Clouds rise. Nearly every ecosystem on the planet depends on the energy arriving from that one star. Beyond Neptune, the light still arrives. The warmth does not. This change is controlled by one of the simplest laws in physics. As sunlight travels away from the sun, it spreads across a larger and larger area, double the distance, and the same amount of energy must cover 4 times as much space, travel 3 times farther, and the light becomes 9 times weaker. This is known as the inverse square law. Its mathematics is simple. Its consequences are merciless. Earth orbits 1 astronomical unit from the sun. At that distance, every square meter facing the sun receives roughly 1,360 watts of solar energy before the atmosphere absorbs or reflects part of it. That energy powers the climate, the oceans, and almost every food chain on the planet. Neptune orbits about 30 times farther away. Sunlight there is not 30 times weaker. It is about 900 times weaker. And once the spacecraft moves beyond Neptune, the decline continues. At Pluto's average distance, sunlight is roughly 1,600 times weaker than it is at Earth. Farther into the Kuiper Belt, it becomes weaker still. Yet the human eye is extraordinarily sensitive. If you could stand on Pluto's surface at local noon, the landscape would not be completely black. The sun would appear as a small, intensely bright point. It could cast shadows. Under the right conditions, there might be enough light to read by. But the scene would resemble deep twilight more than an Earth afternoon. The sky above you would remain black because Pluto's atmosphere is too thin to scatter sunlight the way Earth's atmosphere does. There would be no blue dome, no warm horizon, no golden light spreading through clouds, only a pale landscape beneath a dark sky, illuminated by a distant point that no longer has the power to warm anything around you. You could face the sun and feel nothing on your skin. That may be the strangest part. The light would tell your eyes that a star is present. The cold would tell the rest of your body that it may as well not be. Surface temperatures across much of the trans-Neptunian region remain between about 30 and 50 kelvins. That is roughly -370 to -400 degrees Fahrenheit. At those temperatures, familiar substances behave in unfamiliar ways. Nitrogen, which forms most of the air you are breathing on Earth, becomes solid ice. Methane, a gas associated with atmospheres and biology, becomes a rigid crystalline material. Carbon monoxide freezes onto the ground. Water ice becomes so hard that it can support mountains. A traveler walking across such a world would not be standing on ordinary rock. The landscape might be built from materials that would vanish into the air under Earth-like conditions. A nitrogen glacier could move through a valley. Methane frost could gather on a mountain. Water could form cliffs that endure for millions of years. The chemistry is familiar. The behavior is alien. The cold also changes how quickly anything can happen. Molecules move more slowly. Chemical reactions become rare. Surface changes may unfold over thousands or millions of years. A mark left on a small, inactive object could remain for an age longer than recorded human history. Even sunlight itself becomes less useful as a source of change. Closer to the sun, ultraviolet radiation can alter surfaces, drive atmospheric reactions, and break molecules apart. Beyond Neptune, the same radiation still reaches the ice, but slowly and weakly. Over billions of years, it can transform simple compounds into dark reddish organic material. The process is patient. A surface may gradually change color under a rain of photons and energetic particles, one molecular bond at a time. The results appear on many distant objects. Some are neutral gray, others are deep red. Their color is not the glow of heat, it is the stain of time. But the weakness of sunlight affects more than landscapes. It determines whether a spacecraft can remain alive. Near Earth, solar panels are an obvious solution. They convert abundant sunlight into electricity. Satellites, space stations, and many planetary missions rely on them. At Mars, solar power is weaker but still practical. At Jupiter, it becomes difficult. A spacecraft needs much larger panels to collect enough energy. Beyond Jupiter, the problem grows severe. By the time sunlight reaches Neptune and the Kuiper Belt, ordinary solar arrays would need to be enormous to produce useful power. Their size would add mass. Their surfaces would need to remain precisely pointed toward a tiny sun. The electricity they generated would still be limited. For the spacecraft traveling here, sunlight has stopped being a dependable fuel. The sun can still illuminate the hull. It cannot keep the instruments running. This is the moment when the spacecraft becomes truly independent from the star it is leaving behind. Its cameras, computers, heaters, transmitters, and scientific instruments must survive on another source of energy. Without electricity, the spacecraft would not freeze instantly. Space itself does not pull heat away as quickly as air or water, but over time, critical components would cool. Electronics would fail. Instruments would become useless. The transmitter would fall silent. The machine would continue moving. It simply would no longer be alive in any meaningful sense. This distinction matters in the outer solar system. Motion does not require power. A spacecraft launched from Earth can coast for centuries under the influence of gravity and inertia. Survival does require power. It needs electricity to think, to measure, to warm itself, and to tell Earth what it has found. The farther it travels, the more carefully that power must be rationed. Some systems must sleep so others can remain awake. A heater may be more important than a camera. A transmitter may need to wait while an instrument collects data. Every watt becomes a decision. Meanwhile, the sun continues to shrink. From Earth, it is a disk wide enough to damage the eye. From Pluto, it is almost point-like. Farther out, its apparent size becomes smaller still, though its brilliance continues to distinguish it from the stars. It remains the central mass of the solar system. Its gravity still controls the broad motion of every distant object around you. But visually, its authority is disappearing. It no longer fills the sky. It no longer creates day in the way humans understand day. It no longer provides useful warmth or power. It becomes a marker, a bright coordinate indicating the direction from which the spacecraft came. Somewhere near that point lies Earth, but Earth itself cannot be seen. Even through powerful instruments, the inner planets are crowded near the Sun from this distant perspective. The entire planetary system behind Neptune occupies a small region of sky. Every human voice, every city light, every radio tower, and every memory of warmth lies in that direction. The Sun points toward them, but it cannot bring them closer. Ahead, the darkness grows. Behind, the light remains. And the spacecraft must now continue through a region where the star that created the solar system can offer guidance, but almost nothing else. The Sun has not vanished. It has become only light, and light alone cannot keep a spacecraft alive. New Horizons does not survive because the space beyond Neptune is gentle. It survives because every part of the spacecraft was designed to expect almost nothing from the environment around it. No air surrounds the hull. No sunlight provides meaningful warmth. No nearby planet offers gravity, protection, or a place to land. The spacecraft carries everything it needs to remain alive, and every year, it carries slightly less of the one resource that matters most: power. Near Earth, sunlight can provide electricity almost continuously. Large solar arrays unfold, face the Sun, and convert a portion of its energy into electrical current. Far beyond Neptune, that solution is no longer practical. The sunlight is too weak. To produce the same amount of power available near Earth, a solar array would need to be hundreds or even thousands of times larger. It would become too massive, too fragile, and too difficult to control. So New Horizons does not depend on sunlight. It carries a radioisotope thermoelectric generator. Inside that generator is plutonium-238, a radioactive material that slowly releases heat as it decays. The spacecraft converts part of that heat into electricity. There are no moving parts inside the generator. No engine turns. No turbine spins. Atoms decay, heat is released, and a small electrical current is produced. That current keeps the spacecraft alive. When New Horizons launched, its generator produced only a few hundred watts of electrical power. That is less than many household appliances use. Yet this small amount had to support the entire mission. The cameras, the computers, the guidance system, the radio transmitter, the scientific instruments, the heaters protecting components from the cold. Every command processed by the spacecraft, every measurement collected, and every bit of data returned to Earth depended on that limited supply. And the supply was never constant. Plutonium-238 decays slowly, which is why it is useful for missions lasting decades. But slow decay is still decay. Each year, the generator produces slightly less heat. Each year, the spacecraft has slightly less electrical power available. Nothing can refill it. No solar panel can replace what is lost. No technician can install a new generator. The spacecraft must adapt. Mission controllers carefully decide which systems can operate and which must remain off. Some instruments cannot be used at the same time. Heaters may need priority over scientific observations. Data may be collected during one period and transmitted much later. The spacecraft lives through a schedule of controlled awakenings and deliberate sleep. During hibernation, many systems are turned off. The spacecraft continues moving but it uses as little power as possible. Only essential functions remain active. Then, at a planned time, New Horizons wakes. Its computers restart normal operations. Its antennas turn toward Earth. Its instruments begin to listen to the environment again. The spacecraft reports that it is still alive, but even this simple message does not arrive immediately. At the distance of the outer Kuiper Belt, a radio signal may need nearly 9 hours to travel from the spacecraft to Earth. That delay changes the meaning of control. On Earth, an engineer can operate a machine and see the result almost instantly. Press a command, watch a response, correct a mistake. With New Horizons, every command becomes a prediction. Mission controllers decide what the spacecraft should do. The instructions are transmitted into space. Then Earth waits. For hours, no one knows whether the command has arrived. When it finally reaches the spacecraft, the machine begins carrying it out. If everything works correctly, a confirmation signal is sent back. Then Earth waits again. A complete exchange can take most of a day. There is no way to steer the spacecraft in real time. There is no way to watch a problem unfold and immediately intervene. By the time mission controllers learn that something has gone wrong, the spacecraft has already been alone with the problem for hours. This is why autonomy is essential. New Horizons must recognize certain failures without help from Earth. If its computer detects an unusual condition, the spacecraft may enter safe mode. Non-essential systems are shut down. The machine turns its antenna toward Earth. It waits for instructions while protecting the power, temperature, and orientation needed for survival. But even safe mode is not truly safe. It is only a controlled attempt to prevent a problem from becoming fatal. If the spacecraft turns in the wrong direction, its antenna may no longer point toward Earth. If a critical heater fails, a component may cool beyond its operating limit. If the computer cannot restart, no engineer can physically reach it. There is no repair mission. There is no rescue vehicle waiting closer to the sun. Even the fastest spacecraft humanity could launch would need years to approach the region where New Horizons is traveling. By then, any emergency would be long over. The machine must save itself or remain silent forever. The darkness outside does not attack the spacecraft. That is what makes the situation so unusual. There are no storms pressing against the hull. No atmosphere causes friction. No ocean crushes the structure. Most of the surrounding space is nearly empty. And yet the environment is deeply hostile to technology. The cold threatens components. Radiation slowly damages electronics. Dust particles can strike at enormous relative speeds. The weak sun cannot provide power. The distance prevents rapid communication. The spacecraft is not fighting a dramatic force. It is fighting time. Every year adds wear. Every year reduces available power. Every year increases the communication delay as the spacecraft moves farther away. The radio signal arriving at Earth also becomes weaker with distance. Like sunlight, radio energy spreads outward. By the time New Horizons transmission reaches Earth, the signal is unimaginably faint. It carries far less power than the background electrical noise produced by ordinary equipment. To detect it, NASA uses the Deep Space Network, a system of enormous radio antennas positioned around the world. These antennas must point with extraordinary precision. They listen to a tiny region of the sky. Then, sensitive electronics separate the spacecraft's signal from the surrounding noise. The process is slow. New Horizons cannot send data at the speed of a home internet connection. Even under favorable conditions, the transmission rate is measured in only a few thousand bits per second. An image taken in a fraction of a second may require hours to send. A large scientific dataset may take months. After the Pluto flyby, New Horizons needed more than a year to return all of the stored observations to Earth. The spacecraft had collected the information quickly as it passed the dwarf planet at high speed. But the distance between Pluto and Earth created a narrow channel through which that information had to travel. The encounter lasted hours. The return of the data lasted more than a year. This creates a strange separation between discovery and understanding. The spacecraft sees first. Humanity learns later. New Horizons may already have completed an observation, while Earth is still receiving data from an earlier one. The machine continues through the darkness, carrying knowledge that no person has yet examined. In this sense, the spacecraft is more than a distant instrument. It is a temporary archive, a small collection of computers moving through the outer solar system, holding measurements inside electronic memory until they can be delivered across billions of miles. Every successful transmission reduces that isolation slightly. A signal reaches Earth. The data are reconstructed. An image appears. A graph takes shape. For a moment, the distance between the spacecraft and its makers becomes visible in the information it has returned. Then the antenna turns quiet again. New Horizons continues outward. Its power continues to decline. Its instruments wait for the next scheduled observation. And somewhere inside the spacecraft, one of its smallest devices continues recording tiny impacts from particles too small to see. The surrounding space was expected to become cleaner as the spacecraft moved beyond the main Kuiper Belt. The dust should have become less common, but the impacts did not fade as quickly as expected. In the deepest darkness beyond Neptune, the spacecraft was still being touched by something the maps had not fully accounted for. The particles are almost unimaginably small. Most are far too tiny to be seen by a camera. Some are no larger than grains of smoke. Others are microscopic fragments of ice and rock moving through the darkness at thousands of miles per hour. To the spacecraft, they are nearly invisible, but they are not silent. Space itself cannot carry sound, yet every time one of these particles strikes the dust detector aboard New Horizons, the impact produces a tiny electrical pulse. A brief signal, a microscopic event recorded by a machine billions of miles from Earth. The instrument is called the Venetia Burney Student Dust Counter, named after the young girl who suggested the name Pluto in 1930. It is one of the smallest scientific instruments on New Horizons, and it has been listening to the dust of the solar system for nearly the spacecraft's entire journey. As New Horizons traveled away from the Sun, the detector counted impacts. Near the inner planets, dust came from asteroids, comets, and collisions throughout the planetary system. Farther out, the sources changed. Beyond Neptune, much of the dust is expected to come from the Kuiper Belt itself. Although the large objects there are separated by enormous distances, they are not completely isolated. Small bodies sometimes collide. Interstellar particles arriving from outside the solar system strike their frozen surfaces at high speed, knocking loose tiny fragments. Each collision releases material. Those fragments become part of a thin cloud spread throughout the region. The cloud is extraordinarily sparse by ordinary standards. A human drifting through it would not see a haze. No layer of dust would gather on a window. The surrounding space would still appear perfectly clear, but over months and years, an instrument with enough patience can detect the individual impacts. Before New Horizons entered the outer Kuiper Belt, scientists had models describing how the dust should be distributed. The general expectation was straightforward. Dust density should rise as the spacecraft entered regions containing more parent bodies. It might reach a maximum near the heart of the classical Kuiper Belt, where many icy objects follow relatively stable orbits. Then, beyond the belt's traditionally accepted outer edge, the dust should begin to decline. Fewer parent bodies should mean fewer collisions. Fewer collisions should mean less dust. The spacecraft would gradually move into a cleaner and emptier environment. But the detector did not record the expected decline. As New Horizons traveled beyond 50 astronomical units from the Sun, dust continued striking the instrument. The impact rate remained higher than several models had predicted. The difference was not dramatic enough to create a visible storm around the spacecraft. Nothing outside suddenly changed appearance. The mystery existed only in the numbers. Tiny impacts continued arriving from a region that was expected to contain less material. A few electrical pulses were suggesting that the map might be incomplete. There are several possible explanations. The first involves the dust grains themselves. Dust in the outer solar system is not necessarily made from simple, solid rock. Many particles may contain frozen water, carbon dioxide, methane, or other volatile compounds. Even weak sunlight can slowly alter them. Ultraviolet radiation can erode the icy material, reducing the size and mass of a grain. As the particle becomes smaller, pressure from sunlight can influence it more strongly. The force is extremely weak, but the particle is also extremely light. Over long periods, radiation pressure may push some grains farther outward than earlier models assumed. In this case, the dust detected by New Horizons may have been created deeper inside the Kuiper Belt and then transported outward. The parent objects would remain within the known population. Only their dust would travel farther. A second explanation is closely related. The composition of the grains may cause them to respond differently to sunlight, heat, and radiation than the simpler particles used in some early models. A grain made partly from volatile ice does not evolve in the same way as a grain made entirely from durable mineral material. It may shrink. It may lose a coating. Its orbit may gradually change. If thousands of such particles behave differently from expectations, the entire dust cloud could extend farther into space. These possibilities may explain at least part of the excess. But there is another explanation, and it carries a larger consequence. The dust may be coming from objects we have not yet seen. If a hidden population of small icy bodies exists beyond the traditional edge of the Kuiper Belt, those bodies would continue producing debris. They would collide occasionally. They would be struck by interstellar dust. Their surfaces would release particles into the surrounding space. New Horizons would detect those particles even if telescopes near Earth could not see the bodies that created them. This does not require a hidden planet. It does not require an enormous unknown object waiting in the darkness. It may require only more small worlds. Dark objects orbiting at 60, 70, or 80 astronomical units could remain below the detection limits of most surveys, especially if they are small, unusually dark, or traveling on paths away from the regions astronomers observe most frequently. Individually, they would be almost impossible to find. Collectively, their dust could reveal their presence. It would be a little like entering a dark room and noticing particles floating in a beam of light. You may not see the objects that release them, but the dust tells you that something is there. The important word is may. The measurements do not prove that a second Kuiper Belt exists. They do not prove that the known belt continues smoothly into the darkness. Dust is complicated. Particles respond to forces that have almost no effect on larger bodies. Their size, shape, composition, and electric charge can all change the paths they follow. Several processes may be operating at the same time. Some grains may have drifted outward from the known belt. Some may have been altered by radiation. Some may have entered from interstellar space. And some may have been created by objects our telescopes have not yet found. The detector cannot tell us which explanation is correct simply by counting impacts. It can only tell us that the environment is not behaving exactly as expected. That alone matters. For decades, the apparent decline in known objects beyond about 50 astronomical units was treated as evidence of a real outer edge. The number of discoveries dropped, so the population itself appeared to drop. But every astronomical survey has limits. At greater distances, objects receive less sunlight. They reflect less light back toward Earth. Their apparent motion becomes slower. A body that would be detectable at 40 astronomical units may disappear completely from our surveys at 80. The edge in the catalog may not be an edge in space. It may be the distance at which our telescopes begin to fail. New Horizons offers a different way to examine the problem. It does not need to see the distant bodies. It is already inside the environment. It can feel the particles those bodies may have produced. Each impact is small, but together they form a message. The region beyond the known Kuiper Belt may not be as empty as it appears. Somewhere in the darkness, unseen surfaces may be slowly losing material. Hidden objects may be colliding. Ancient fragments may be orbiting too far away for reflected sunlight to reveal them. The spacecraft cannot turn and show us where they are. Its dust counter provides no image, only a sequence of electrical pulses arriving from invisible particles. And so the mystery remains quiet. No dramatic discovery appears in a photograph. No new world fills the screen. Instead, a machine traveling far beyond Neptune continues to register tiny impacts from a region that should have been growing empty. The dust does not prove what is waiting ahead. It reveals something more unsettling. We may have confused the limit of our vision with the limit of the solar system. The solar system has not become empty. It has become difficult to observe. From Earth, the space beyond Neptune appears almost perfectly black. The objects moving through it produce no light of their own. They can only be found when sunlight travels outward, strikes their frozen surfaces, and reflects back across billions of miles toward a telescope. Very little light completes that journey. A distant Kuiper Belt object is punished twice by distance. First, it receives only a tiny fraction of the sunlight available near Earth. Then, the small amount it reflects must travel all the way back to us. By the time those photons reach a telescope, the object may appear millions of times fainter than the dimmest star visible to the human eye. A world hundreds of miles wide can be reduced to a single uncertain pixel. A smaller body may leave no detectable signal at all. This means that the apparent darkness ahead of New Horizons cannot be trusted. It does not tell us what is absent. It tells us what our instruments are unable to see. Finding a trans-Neptunian object usually begins with several images of the same region of sky. At first, every point appears fixed. Stars fill the foreground. Behind them lie galaxies so distant that their light began traveling toward Earth before human beings existed. Hidden among those thousands of stationary points may be one object belonging to our own solar system. The only obvious difference is movement. But that movement is painfully slow. Objects close to Earth can cross the sky quickly. Asteroids may shift enough between images to reveal themselves almost immediately. A body beyond Neptune may move only a tiny fraction of a degree over many hours. In a single exposure, it resembles an ordinary star. Astronomers must compare one image with another, searching for a point that has moved slightly, while everything around it appears unchanged. The shift may be so small that software must test many possible directions and speeds before the object becomes visible. Images can be digitally aligned along a predicted path and stacked together. Background stars blur or fade, while a genuine moving object grows brighter. This technique can reveal worlds too faint to appear clearly in any single photograph. But the search is difficult. A deep image may contain thousands of galaxies, detector artifacts, cosmic ray strikes, and electronic noise. Each false signal must be separated from a real object moving through the outer solar system. And finding a point of light is only the beginning. One observation does not provide a reliable orbit. Astronomers must return to the object again and again, sometimes over several years. Its position changes slowly, and only a longer arc of motion reveals where it is truly going. Without enough follow-up observations, the object can become lost. Its predicted position spreads across a larger region of sky until no telescope knows exactly where to look. Some distant bodies may have been photographed without being recognized. Their light may already exist inside old astronomical archives, buried among millions of other sources, waiting for better software or a future observation to reveal that one faint point was moving. The problem becomes worse with distance. Imagine two objects of identical size and color. One orbits 40 astronomical units from the Sun. The other orbits 80. The second object receives only about 1/4 as much sunlight. It is also roughly twice as far from the telescope observing it. The light returning from its surface weakens again across that greater distance. The result is severe. Moving a body twice as far away can make it many times harder to detect. At 80 or 90 astronomical units, even objects hundreds of miles wide may become invisible to ordinary surveys. Smaller bodies can exist in large numbers without appearing in our catalogs. This creates a powerful observational bias. The Kuiper Belt, we know, is dominated by the objects easiest to find. They tend to be larger, brighter, closer to the Sun, or positioned near the broad plain where astronomers have historically searched. A dark object on a highly tilted orbit could spend most of its existence far above or below that region. A distant world might pass through the surveyed area only briefly during an orbit lasting centuries. If no telescope happens to be looking at the correct place during that time, the object remains unknown. This is why the outer solar system may look sharply defined on a map. The number of known objects falls beyond a certain distance, creating what appears to be an edge. But the decline could partly reflect the increasing difficulty of discovery. The population may not stop. Our vision may simply lose it. A lighthouse beam crossing a dark ocean can reveal nearby ships. Farther away, equally large vessels disappear beneath the horizon and the limits of the light. Their absence from view does not mean the ocean has ended. The same warning applies beyond Neptune. Our maps show the territory that sunlight and technology have allowed us to detect. They do not necessarily show the entire territory. New observatories are beginning to improve that picture. The Vera C. Rubin Observatory was built to photograph enormous regions of the southern sky repeatedly. Instead of observing one distant object at a time, it surveys the sky again and again, creating a moving record of anything that changes position or brightness. This repeated coverage is especially valuable for the outer solar system. A faint trans-Neptunian object may be almost impossible to recognize in one image. Across hundreds of observations, its slow path can emerge. Rubin is expected to reveal many thousands of objects that earlier surveys missed. Some will belong to familiar Kuiper Belt populations. Others may occupy unusual resonances with Neptune. Some may travel on highly elongated paths through the scattered disk. A few could belong to more distant populations, whose existence is currently suggested only by incomplete observations and unexplained dust. The value is not simply in increasing the number of known objects. A much larger catalog can reveal structure. If the Kuiper Belt truly ends near its traditional boundary, the new observations should confirm a genuine decline. If objects continue farther outward, repeated surveys may expose them. If their orbital directions form real patterns, those patterns should become stronger as the sample grows. If the apparent patterns were produced by where telescopes happen to look, they may disappear. More data can turn a mystery into a discovery. It can also turn an exciting idea into an illusion. That is the quiet power of a survey. It does not search only for what scientists hope to find. It measures the sky repeatedly and allows the structure to reveal itself. Yet even Rubin cannot see everything. No telescope can collect light that never arrives. Bodies below a certain size or brightness will remain hidden. Objects much farther away may be too faint even for the most sensitive surveys. Some regions of the sky are crowded with stars, making slow-moving points difficult to separate from the background. Weather, observing schedules, and the brightness of the moon can interrupt the search. And every telescope near Earth is still looking from the same general position, deep inside the planetary system, trying to detect small dark bodies through reflected sunlight. This is what makes New Horizons so valuable. The spacecraft does not have the power or instruments to conduct a complete survey of the region around it. It cannot photograph every hidden object. But it is physically present in the environment our telescopes are trying to understand from far away. Its dust detector can register evidence that light-based surveys miss. Its instruments can measure particles, plasma, and radiation where those things actually exist. The spacecraft and the telescopes are observing different pieces of the same puzzle. Earth sees faint points of reflected light. New Horizons feels microscopic impacts in the darkness. When both suggest that material may continue beyond the expected boundary, the possibility becomes harder to dismiss. Still, the map remains unfinished. Thousands of objects have been discovered, yet they may represent only the visible surface of a much larger population. Somewhere ahead, worlds may be following orbits that have never been calculated. They may have moons no telescope has resolved. They may preserve materials unchanged since the first few million years of the solar system. They may pass through the darkness for centuries without reflecting enough light for Earth to notice. And among the few distant objects we have managed to find, some follow paths that Neptune cannot easily explain. Their orbits appear to remember a force that is no longer visible. Perhaps a star once passed near the young sun. Perhaps a planet was lost. Or perhaps something massive is still moving through the darkness, too distant and too faint for any telescope to see. The limits of our vision hide objects, but the orbits of the objects we can see may reveal what touched them long ago. Somewhere beyond the familiar Kuiper Belt, an object called Sedna moves through an orbit that seems almost impossible. It does not travel near Neptune. It does not pass through the crowded inner regions of the outer solar system. Even at its closest point to the Sun, Sedna remains more than twice as far away as Neptune. Then it turns outward again, far outward. Its path carries it hundreds of astronomical units into the darkness, before gravity slowly bends it back toward the Sun. One complete orbit takes more than 11,000 years. The last time Sedna occupied roughly the same place in its orbit, agriculture had not yet begun across much of Earth. Cities did not exist. Written language was still thousands of years away. Sedna moves on a timescale that makes human history appear brief. But its distance is not the greatest mystery. The mystery is how it arrived there. Neptune can scatter objects. A small icy world passing close to the planet may gain energy and be thrown into a long, stretched orbit. This process explains many members of the scattered disk. But Sedna never comes close enough to Neptune. Its nearest point remains far beyond the region where the planet could have given it such a powerful gravitational push. Neptune's influence is too weak. The known giant planets cannot easily explain the orbit. Something else must have changed it. An orbit is more than a path. It is a record of every important gravitational encounter an object has experienced. Impacts can alter surfaces. Radiation can change colors. Ice can flow, freeze, or escape. But the broad shape of an orbit can survive for billions of years. Sedna may therefore preserve evidence of an event from the solar system's earliest history. A force touched it. The force is no longer obvious, but the path remains. One possibility begins with the birth of the Sun. Today, the Sun travels through the Milky Way with neighboring stars separated by enormous distances. The closest stellar system is more than 4 light-years away. But the Sun may not have formed in isolation. Like many stars, it was probably born inside a cluster containing dozens, hundreds, or perhaps thousands of young stars. These stars may have formed from the same enormous cloud of gas and dust. Inside that crowded nursery, close encounters would have been much more common. Another star may have passed near the young solar system, not close enough to disturb the inner planets, not close enough to pull Earth away from the Sun, but close enough to affect small bodies orbiting far outside Neptune. The passing star's gravity could have lifted their closest approaches away from the giant planets, leaving them stranded on detached orbits. Sedna may be a fossil from that encounter. If so, its orbit carries the faint gravitational fingerprint of a star that passed near the Sun more than 4 billion years ago and has since vanished into the galaxy. That star could now be thousands of light years away. It may no longer exist in the same form. Yet Sedna would continue following the path it helped create. Another possibility is more violent. The early solar system may once have contained an additional large planet. Models of planetary formation often produce more giant worlds than the 4 that remain today. During the unstable early history of the solar system, gravitational encounters between planets could have pushed one of them outward. The missing world may have scattered smaller objects as it moved. Then another encounter may have ejected the planet completely. If this happened, a planet larger than Earth could have wandered between the young giant planets, altered the outer debris field, and then escaped into interstellar space. Sedna's orbit could be one of the few surviving traces of that lost world. The planet itself would now be gone. The objects it disturbed would remain. There is also a third possibility. The planet may not be gone. It may still exist. The idea is usually called Planet 9. The hypothesis does not begin with a photograph of an unknown world. No telescope has directly seen such a planet. It begins with orbits. Several extremely distant objects appear to share certain patterns in the directions and shapes of their paths. If those patterns are real, the gravity of a large unseen planet could help explain them. The proposed world would not resemble Pluto. It would be far more massive, perhaps several times the mass of Earth. It might orbit hundreds of astronomical units from the Sun, taking many thousands of years to complete a single revolution. At such a distance, it would receive almost no sunlight. Even a planet much larger than Earth could appear as a faint point, moving extremely slowly against the stars. A telescope might photograph it without recognizing it. The image could remain hidden inside a survey archive, indistinguishable from countless distant stars, until years of observations revealed its motion. But Planet 9 remains a hypothesis. The current sample of extreme trans-Neptunian objects is small. Their apparent orbital patterns may be affected by where telescopes have searched and where they have not. Astronomers are more likely to find objects in some parts of the sky than others. Weather, seasons, the Milky Way's bright background, and the locations of major observatories all influence the regions that receive the deepest surveys. A pattern in the catalog may reflect a pattern in nature, or it may reflect a pattern in observation. Each newly discovered distant object can change the conclusion. Some strengthen the case for an unseen planet. Others do not fit neatly into the expected alignment. This is why more discoveries matter so much. A hidden planet would influence many objects, not just one or two. With a large enough sample, its gravitational signature should become clearer. If the patterns remain, Planet 9 becomes more convincing. If they dissolve, another explanation will be required. Perhaps a passing star shaped these orbits. Perhaps a planet once existed and was lost. Perhaps the early disk of material beyond Neptune behaved in a way our models do not yet capture. Or perhaps several processes acted together. The outer solar system does not promise a single answer. It preserves many layers of history. Sedna may have been affected by the stellar cluster in which the Sun was born. Another object may have been scattered by Neptune. A third may preserve the influence of an unknown planet. What appears to be one distant population may contain survivors of completely different events. From the spacecraft, none of this history is visible. Sedna would not loom ahead like a mysterious world. It would be a faint point, probably too distant to see without a powerful instrument. Planet 9, if it exists, would be even harder to identify. The darkness would look unchanged. That is the unsettling nature of gravity. A massive object does not need to shine to shape the space around it. It can remain invisible while its influence spreads across billions of miles. Or it can disappear entirely, leaving altered orbits behind. The objects beyond Neptune may therefore be moving through a landscape shaped partly by things we cannot see and events we did not witness. Their paths are the evidence. But the author of those paths remains uncertain. And even Sedna's enormous orbit does not bring us close to the true outer boundary. Beyond it, the solar system opens into regions so vast that every edge we have crossed begins to look like only another beginning. The farther you travel beyond Neptune, the less useful the word edge becomes. At first, Neptune seems like the obvious boundary. It is the final planet. Beyond it, the familiar sequence ends. But the orbit of a planet is not a wall. Crossing Neptune's path does not mean leaving the solar system. It only means leaving the region dominated by the 8 major planets. Farther out lies the main Kuiper Belt. For decades, this broad population of icy objects appeared to fade near 50 astronomical units from the Sun. That distance was often treated as another edge. But the scattered disk continues beyond it. Its objects follow long, unstable paths that may carry them hundreds or even thousands of astronomical units away before returning. Then there are detached objects like Sedna, whose orbits remain so distant that Neptune can no longer explain them easily. Each new layer extends the solar system farther into the dark. And still, none of these boundaries marks the final end. A spacecraft traveling outward eventually approaches another kind of frontier. The Sun does more than produce light and gravity. It also releases a continuous flow of charged particles called the solar wind. These particles stream outward through the planetary system, carrying the Sun's magnetic field with them. Together, they create an enormous bubble around the Sun known as the heliosphere. Earth, Neptune, Pluto, and much of the Kuiper Belt all exist inside this bubble. The heliosphere is not perfectly round. The Sun moves through the thin material between the stars, and the surrounding interstellar environment presses against the solar wind. The exact shape is complex and still being studied. But somewhere far beyond the planets, the outward pressure of the solar wind becomes too weak to dominate. The flow slows. It becomes turbulent. Then, at a boundary called the heliopause, the solar wind gives way to the material between the stars. Voyager 1 crossed this boundary in 2012. Voyager 2 crossed it in 2018. Both spacecraft had traveled far beyond Neptune. When their instruments detected the change, they became the first human-made objects to enter interstellar space, according to the definition based on the Sun's particle environment. But even then, they had not escaped the solar system in every sense. The Sun's gravity still held them. They were still moving through a region containing objects bound to the Sun. They had crossed the edge of the heliosphere. They had not crossed the outermost reach of the Sun's domain. This is where the definition becomes difficult. Where does the solar system truly end? Is it where the planets stop? Where the Kuiper Belt fades? Where the solar wind disappears? Or where the Sun's gravity becomes too weak to hold distant objects? Each answer describes a different boundary, and each boundary lies at a different distance. The farthest may belong to the Oort Cloud. No spacecraft has seen it. No telescope has photographed it as a complete structure. Its existence is inferred from long-period comets that arrive from every direction in the sky. These comets follow enormous orbits. Some may spend thousands or millions of years traveling far from the Sun before falling inward. Because they approach from many different directions, astronomers believe their source is not a flat belt like the Kuiper Belt. It may be a vast spherical cloud surrounding the entire solar system. The inner part of this cloud could begin thousands of astronomical units from the Sun. Its outer regions may extend tens of thousands of astronomical units farther. Some estimates place the farthest objects near 100,000 astronomical units away. At that distance, the scale of the planetary system becomes almost meaningless. Earth orbits at 1 astronomical unit. Neptune orbits at about 30. The main Kuiper Belt reaches only a little farther than 50. If the Oort Cloud extends to 100,000 astronomical units, then Neptune lies extremely close to the Sun, compared with the full reach of the solar system. Imagine shrinking the distance from the Sun to Earth to 1 foot. Neptune would orbit about 30 feet away. The main Kuiper Belt would end somewhere around 50 feet. But the outer Oort Cloud could extend nearly 19 miles in every direction. On that scale, every planet would fit inside a small yard. The full gravitational frontier would surround an entire city. This changes the meaning of the journey. A spacecraft crossing Neptune's orbit may feel unimaginably distant from Earth. But compared with the possible size of the Oort Cloud, it has barely begun to leave. Even Voyager 1, the most distant human-made object, remains deep inside the Sun's larger gravitational territory. It has crossed into interstellar space, as measured by particles. But it may take tens of thousands of years before it travels through the region associated with the inner Oort Cloud, and far longer before it reaches the distances where the Sun's grip truly fades. At the outer boundary, gravity becomes delicate. An object may still orbit the Sun, but only weakly. A passing star can disturb it. The tidal pull of the Milky Way can slowly alter its path. A small gravitational change may send it inward toward the planets, or outward into permanent interstellar space. The distant edge of the solar system is therefore not a stable wall. It is a region of negotiation. The Sun pulls inward. The galaxy pulls from outside. Passing stars briefly reshape the balance. Some objects remain. Others are lost. Some may even be captured from neighboring stars. There may be no exact line where ownership changes. Only a vast region where the Sun's influence becomes weaker until it can no longer be clearly separated from the gravity of the galaxy around it. The idea of a clean edge belongs to maps. Nature offers transitions. Neptune marks the end of the major planets. The Kuiper Belt marks a population of ancient icy bodies. The scattered disk carries objects into far wider orbits. The heliopause marks the fading of the solar wind. The Oort Cloud may mark the farthest objects still loosely bound to the Sun. Every boundary answers one question. None answers all of them. From the spacecraft, these transitions would remain invisible. No wall would pass over the hull. No light would change color. No sound would announce that one region had ended and another had begun. The stars would appear almost the same. The Sun would continue shrinking. Only the instruments would reveal that the surrounding particles had changed, that the solar wind had weakened, or that the spacecraft was entering a different environment. This may be the most unsettling truth of the outer solar system. You could cross one of its most important boundaries and never know it by looking outside. And even after crossing, another boundary would still wait farther ahead. Neptune was not the edge. The Kuiper Belt is not the edge. The heliopause is not the edge in every sense. And the Oort Cloud, if it extends as far as current models suggest, may not end in a sharp border at all. The solar system does not stop. It fades. Its light weakens first. Then its wind. Then the density of its distant objects. Finally, even its gravity becomes difficult to separate from the darkness between the stars. Behind the spacecraft, Neptune has disappeared completely. Ahead, there is still no final wall, but the sun remains visible, a small, brilliant point marking the direction of everything the spacecraft has left behind. The last familiar planet is gone. The direction of home is not. New Horizons continues to move. There is no engine burning behind it. No visible trail marks its passage. The spacecraft simply follows the motion given to it decades ago, carrying human instruments deeper into a region no human being has ever entered. Behind it lies Neptune, now lost among the stars. Farther behind lie all the other planets: Jupiter with its storms, Saturn with its rings, Mars with its silent deserts, Earth with its oceans, weather, cities, and billions of lives unfolding beneath a warm sun. From this distance, none of them can be seen with the naked eye. They have collapsed into the same direction. Home is no longer a world in the sky. It is a coordinate. The sun still marks that coordinate. It remains the brightest point visible from the spacecraft, a sharp white light that cannot be mistaken for any ordinary star. But almost everything that once made it feel like the sun has been left behind. Its warmth disappeared first. Then its usefulness as a source of power. Farther out, even the solar wind begins to weaken, thinning until it finally gives way to the particles between the stars. The sun's gravity remains, but it too becomes gentler with distance. There is no single moment when the spacecraft becomes completely free of home. Home simply grows weaker. This has been the pattern of the entire journey beyond Neptune. Nothing ends suddenly. Everything fades. The planets disappear from view. The space between known worlds expands. The light weakens. Radio messages take longer to arrive. The spacecraft's power slowly declines. The boundaries on the map become less certain. And every time one apparent edge is crossed, another appears farther ahead. The Kuiper Belt was once imagined as the final band of debris surrounding the planets. Then the scattered disk extended beyond it. Sedna revealed orbits even more distant. The heliopause marked the end of the solar wind, but not the end of the sun's gravity. And the possible Oort Cloud opened the solar system into a sphere so enormous that Neptune seemed close to the sun by comparison. There was never one edge. Only layers of departure. New Horizons is still moving through one of those layers now. Its instruments continue to measure dust, particles, and faint traces of the sun's influence. Its generator produces a little less electricity each year. Eventually, difficult choices will have to be made. One instrument may be turned off to preserve another. A heater may receive power that once belonged to a camera. Scientific observations will become less frequent. The spacecraft will spend longer periods asleep. Then, one day, there may not be enough power to awaken everything again. The transmitter may fall silent. No dramatic explosion will mark the end. The spacecraft will continue traveling. Its antenna may remain pointed toward a world that can no longer hear it. Its instruments will become cold and inactive. Its memory will hold whatever final measurements were never transmitted. The machine will no longer send messages, but it will not stop. For millions of years, New Horizons will drift through the galaxy. The sun will become another star behind it. Its metal surfaces will be struck by dust and radiation. Its trajectory may be altered slightly by the gravity of distant stars. Long after the civilizations that built it are gone, the spacecraft may continue carrying evidence that human beings once looked beyond their final planet and chose to keep going. That future lies far ahead. For now, New Horizons is still alive. Signals still cross the darkness. Each one leaves the spacecraft and travels inward for hours before reaching the enormous antennas of the Deep Space Network. A pulse arrives. A computer recognizes it. Data gathered billions of miles away become readable on Earth. For a moment, the distance is crossed. The spacecraft tells us what the darkness feels like. It tells us that dust continues farther than expected, that the solar wind is weakening, that the outer solar system remains active, structured, and incomplete. But every answer makes the unknown region larger. We learned that Pluto was not a dead world. We learned that Arrokoth preserved a gentle beginning. We learned that the Kuiper Belt may not fade where older maps placed its edge. We found objects on orbits that Neptune cannot easily explain. And we discovered that the solar system's true frontier may extend almost halfway toward the nearest stars. The space beyond Neptune is not worse because it contains a hidden threat waiting to destroy anything that enters. It is worse because the protections of the inner solar system no longer apply. Sunlight cannot keep a spacecraft alive. Earth cannot respond in time. Rescue is impossible. The nearest known world may be millions of miles away, and the map cannot promise that everything ahead has already been found. It is a region filled with objects we cannot see, histories we cannot reconstruct, and boundaries that refuse to remain fixed. Yet it is still part of our home system. That may be the most unsettling thought of all. Humanity has mapped continents, crossed oceans, placed instruments on other planets, and observed galaxies whose light has traveled for billions of years. But within the gravitational reach of our own sun, enormous regions remain almost entirely unexplored. There may be countless small worlds beyond Neptune that no telescope has detected. There may be distant populations suggested only by dust. There may be remnants of stars that passed near the young sun. There may be evidence of planets that were lost, or one planet still hidden in the dark. The truth is not waiting at one final destination. It is scattered across billions of miles. New Horizons moves through that unfinished map alone. Behind it, the sun points toward Earth. Ahead, the darkness offers no landmark. And between them, a human-made machine carries the faintest connection between what we know and what still remains unseen. Neptune was the last familiar world. It was never the end. Beyond it, the solar system continues to grow colder, darker, and more difficult to understand. The sun remains visible. Its gravity still reaches outward. Its light still shows the direction of home. But warmth, conversation, rescue, and certainty have all been left behind. And somewhere ahead, beyond every boundary we have named, the solar system does not end. It simply becomes too dark for us to know where the ending truly is.